To find the rectangular coordinates of, well, let's pose the question first. How do we find the rectangular coordinates of 3 pi over 6, 5 2 pi over 3, negative 3 pi over 4? You should pause and attempt to find the rectangular coordinates of these points. Now this assumes that the x-axis is along the polar axis and that the pole is at the origin of your xy coordinate system. So under those circumstances, what are the coordinates of 3 pi over 6? What's the x coordinate? What's the y coordinate? And then the same for these. Pause and do that, at least for the 3 pi over 6, because that's the one we're going to look at. Okay, now the point 3 pi over 6 is going to lie at an angle of pi over 6 with respect to the polar axis. The polar axis, again, as we said, is identified with the x-axis, and the pole with the origin of the coordinate system, so that the point lies right here at distance 3 from the pole. What's that tell us? Well, in red here we've drawn the right triangle that corresponds to this point on the xy coordinate system. From the right triangle definition or from the circular definition, this thing, of course, lies at an angle of pi over 6 on a circle of radius 3. We see that the y and x coordinates are just given by the trigonometric relationships. Y is going to be 3 sine pi over 6. X is going to be 3 cosine pi over 6. So this gives us a very simple way of determining the rectangular coordinates of a point given in polar coordinates. 3 pi over 6 in polar coordinates is going to be 3 cosine pi over 6, 3 sine pi over 6 in rectangular. And of course we generalize this way. Okay, if we're at displacement r and angle theta, then x equals r cosine theta and y equals r sine theta. So you could just plug 5 in for r and 2 pi over 3 for theta and get the x and y coordinates of 5, 2 pi over 3. Negative 3 pi over 4 works just the same. We put a negative 3 in for r, and that takes care of the fact that the displacement is in the opposite direction to the pi over 4 direction, and we get the accurate coordinates. This point is clearly in the third quadrant, as we've seen, and you'll get negative values for x and y if you just plug in to these relationships here. Okay, now if we have rectangular coordinates 3, 4, and negative 5, 7, how do we find the polar coordinates? Don't look at the solution down here. Just go ahead and take the point 3, 4 and see if you can determine what its polar coordinates ought to be, and then repeat that for negative 5, 7. Pause and do that. Now I assume that you've paused and you're back. So the point 3, 4 in rectangular coordinates, well, we come out 3 units in the x direction, 4 units in the y direction, and there's our point. R is the distance from the pole, and we've indicated the polar coordinates now in red. R is the distance from the pole, or displacement from the pole, and theta is the angle with respect to the polar axis, which again we identify with the positive x-axis, just as the pole is identified with the origin. And then from the sides of this triangle, which are 3 and 4, we see that r, which is the hypotenuse, has to be found by the Pythagorean identity, the square root of 3 squared plus 4 squared. And your angle theta is the inverse tangent of 4/3, the opposite over the adjacent side, or the y over the x, depending on whether you're using the triangle or circular definition of the sine and cosine. Now to do negative 5, 7, you're going to do something very similar. I'm not going to work that one out for you, but I'll just say that when you do negative 5, 7, of course, you've got to be warned, you do end up in the second quadrant, so you've got to be careful about your angle theta, because the inverse tangent gives you an angle, remember, in either the fourth or the first quadrant. It doesn't give you an angle in the second quadrant. You're getting the fourth quadrant version of the angle when you do the inverse tangent here. So you have to make the obvious adjustment there, and of course you can read about that in the notes, maybe you already have.